All right. So today, inshallah, we will continue discussing the aspects of Chapter 5, which is about stereochemistry. I hope everything is clear now, the board and so on. Just move it a little bit more. Okay. Now, last time we have discussed the rules for determining the absolute configuration of a compound. Let me first save it in case. All right. The last time, as I said, we have discussed the rules for determining the absolute configuration around a stereocenter. Since we do have four different atoms or groups, we said we need first to assign priority of these groups. So the highest of the priority, it will be number 1, the second will be number 2, the third will be number 3, and the fourth will be number 4. Yes, please.
And the fourth is not G. Can you?
Is it more clear now?
Yes.
All right. Sure. Okay. So as I said, these are the four atoms or the four groups which are attached to the stereocenter, and we said we need to determine the priority. We need to prioritize these atoms or groups, and we said those. We said always we first check the atomic number of the directly attached atoms. If we can simply prioritize these atoms, then it's fine. If not, then we should proceed further for the next atom and so on and so forth. All right. Okay, so please, the rules here, they are very important, extremely important actually to see them. Now, after we determine the four atoms or groups, the third rule here will be we must view the molecule. We must view the molecule in such a way that the least priority atom is farthest away from our vision. So after we determine the absolute configuration of, after we determine the priority of the four atoms or groups which are attached directly to the stereocenter, here we must view the molecule. We have to imagine the molecule in three-dimensional way, in such a way that the least priority atom is farthest away from our vision. Now, in this case here, what you have to see, let me just remind you with the terminology and the meaning of each bond. The line here, it means, as we said, this means this bond here, I may draw it here, this bond here is on the same plane. This bond here means it is above the plane, and this bond here means below. So these must be always in our vision. Now, where I have to view this molecule according to this rule? According to this rule, we must view the molecule from this side. So we must imagine that we are looking at this molecule from this side. When you view this molecule at this side, what you will see? Imagine that this is simply the priority of the four atoms around the stereocenter. What you will see 4 is below, so which is far away from our vision. You will see 3 is above, number 1 to your left, number 2 to your right. So then here, after that, what we have to do, the fourth rule here, we have to make or to imagine a rotation from 1 to 2 to 3, and according to this rotation, if rotation is clockwise, we give it the simple R. If the rotation is counterclockwise, we give it the rotation S. So this is what we have to do. Now here, what you have to do, what you will imagine when you look at the molecule from this view or from this angle, you will see number 1 to your left, number 2 to your right, and then below the plane, above the plane is number 3. So now, according to the rule, we must make a rotation, or we must imagine. We must imagine a rotation from 1 to 2 to 3. Now, according to the result of the rotation, that will be our determination. So, if the rotation is clockwise, that means the absolute configuration of this compound is R. If the rotation is counterclockwise, that means the rotation is S. Now here, when you do this, now there is 2 options for the rotation here. Either from 1 going, let me just show you by the model, it's better actually. Alright, imagine this is simply the model, what we have in here. Now imagine number 4, which is the least priority atom, is the black one here. So as you can see here, I have to view the molecule from this side actually, because we must view the molecule in such a way that the farthest away atom must be away from our vision. So we must look from this side. If you look from any other angle, that's definitely is wrong determination. You will end up with a wrong answer. You follow me? Because the rules here of nomenclature are very strict. You must follow them perfectly. Without simply by invention your own rule, you must simply follow the rule. The rule here, after we determine the priority of the 4 groups or atoms, we must view the molecule in such a way that the least priority atom is farthest away from our vision. Secondly, we must view or make imaginary rotation from group number 1 to 2 to 3. And then according to the result of the rotation, that will be our determination. Now, let me show you this. So this is here, number 4 is farthest away from our vision. So we must look from this side. And when you look at this side, you will see like a triangle. You will see like a wind here, going from a fan, going from 1 to 2 to 3, for example. Now it depends here, where is your 1, where is your 2, where is your 3. Imagine this is 1, and this is 3, and this is 4, as you can see here. This is 1, 2, 3. Alright. So imagine this is 1, 2, and this is 3. And this is 3, it is above the plane, as you can see it here. Above the plane is number 3 here. This is 3, right? And number 1 is there 1. So now, in order to go from 1 to 2 to 3, you must imagine that you have to do a rotation in the space, going from 1, going down the plane, then going to the red, then going to the blue, and then continue the rotation. When you look at the result of this rotation, you will see it counterclockwise. It's against the rotation of the watch, and therefore we call it S in this case. So this absolute configuration of this compound is S configuration. Maria asking about the correct angle. The correct angle, you must view the molecule again far in such a way that this group here is farthest away from your vision. Do you follow me? Yani, imagine this is the model, Maria, and even anyone else. This is the model. Where you have to view this molecule, you must view it from this angle, because imagine the black one is the least priority atom according to the rule. The black one, imagine it is the least priority atom. Now where is the correct angle to view? Which angle is the correct one? There is only one angle, which is from this side here. Do you follow me? Because in this case, this will be farthest away from the vision. Do you follow me? You cannot view it from here. You cannot view it from here. You cannot view it from here. You cannot view it from there. You must view it from here according to the rules of the nomenclature. Got it, Maria? Perfect. So after you view it, you just have to imagine based on the angles here and the orientations of the bonds here. So you can see here, if you make it in your notebook, please, all of you just draw this on a piece of paper, just to repeat it and show it, because this is actually, we can only explain it once, but once you understand it, you should be able to determine any absolute configuration of any chiral compound, regardless of how it is written and in which form has been written. Do you follow me? So let's take another example and see, or take another real example. See, imagine we have this compound. See, this is here. We have CH3, we have CH2, CH3, we have OH, and then we have here a hydrogen. All right? Now, in order to determine the absolute configuration, we want to determine absolute configuration of this compound. In order to determine the absolute configuration, there are rules we must follow. The first rule, as we started in the previous chapter, we must determine the priority of the atoms or the groups. As you can see here, this is the stereocenter which we have. So this is number 1, this is number 2, this is number 3, and this is number 4. Of course, we are not going to repeat ourselves and simply to explain why this is 1, 2, 3, 4, because we have spent the whole previous hour this is simply how to determine absolute configuration. It's one of the sections in the chapter 5. I don't have access now to the PowerPoint presentation. You just open it up and see which section now. Now understand it first, and then you go at home and look at which section is this. Now again, how to, after we determine the priority of the groups or atoms which are attached to the stereocenter, as you can see here, we must view the molecule in such a way that the least priority atom is farthest away from our vision. So this is the way we have to do it, because that's actually the angle where we have to look at the molecule. In this case, what you will see, if you draw it in your piece of paper, what you will see number 1 is below the plane, like, do you follow me? Please draw it and imagine of what I am talking to you. What you will see number 2 to your left and number 3 to your right, right? And then number 1 is below the plane. So according to the rule, we must do a rotation of 1 to 2 to 3. So we must go from downward, going to my left, and then continue. So this will be like this. So this is number 1 is below the plane. I must go to number 2 to my left and then continue. Do you follow me? In order to go from 1 to 2 to 3. This, as you can see, is the opposite. It's the same clockwise direction, and therefore we call it R in this case. Do you follow me? If you have any question about this, please ask now, because as I said, this is like a fundamental knowledge. You must know how to do it actually, because by default, most of the questions in this chapter will be about the absolute configuration and determining the absolute configuration of the compound. Okay, sure, I will repeat it again. Alright, so again, in order to determine the absolute configuration, there are rules. We must follow the rules. And we have written all these rules. But just I'm gonna repeat them to you. First, we must determine the priority of all groups or atoms. Second, we must view the molecule in such a way that the least priority atom is farthest away from our vision. Third, we have to imagine a rotation. And this rotation must be, you cannot do anything else. It must be from 1 to 2 to 3 based on this rotation, because actually you have only two possible rotation, either this way or that way. This way is clockwise, which means R. This way is counterclockwise, which means S. Do you follow me? So there is only two possibilities in this determination. Do you follow me? Now, according to the example here, what we have, after we have determined the priority of the groups or atoms, what you would see when you look at this molecule from this angle, you should imagine that you have group number 2 is to your left and group number 3 to your right. Do you follow me? Because these are on the same plane, so you imagine them like that. Do you follow me? Now, and then when I look at this molecule, and then number 1 is below the plane, because as you can see, number 1 is below the plane here. Do you follow me? Now, in order to go from 1 to 2 to 3, I must start from below the plane. And then below the plane, you have only two directions, either this way or this way. Now, according to the rules, we must go from 1 to 2 to 3. So from 1, which is below the plane, I must go to my left in order to go to 2 first. Because you must, remember, this is one-way direction. You must go from 1 to 2 to 3. Anything, if you commit any mistake during these rules, then definitely whatever you are simply getting is definitely wrong. All right. I am just making it on the board because here Maria is asking about the model. I will repeat it on the model, but just remember my words. You must be able to determine the absolute configuration by any structure, by any three-dimensional structure written to you in the board, which means into 2 dimensions. So you must train yourself to determine it by 2-dimensional. But I'm going to show it to you by 3-dimensional in order to imagine it more. So let's imagine that number 4 is here, is this one. The black one is number 4. Do you follow me? Write it down. Black one is number 4. Right. Now, according to what's written here, number 4 is above the plane, as you can see, and the blue one is below the plane, which is number 1 in this case. So the blue one is number 1, right? And the red one is number 2. The yellow is number 3. This is how it looks like when I view the molecule. Right? Now, what you have to do, you have to look actually from this side. This is the angle where you can or you must view the molecule according to the rule, because we must view the molecule in such a way that the least priority atom is farthest away from our vision. Do you follow me, Maria? So far? All right. Now, here you imagine now again, number 1 is below the plane. Number 2 is to my left. Number 3 is to my right. So there is only one option to go from 1 to 2 to 3. Going from below the plane, going to my left, and then continue. Do you see the rotation? Can you see the rotation? This is the only rotation which is correct. Now this rotation, according to the rotation of the clock, as you can see, this is mimicking or making the same rotation of the clock, and therefore this is clockwise, and that's why we call it R in this case. Do you follow me?
Doctor?
Yes, please.
كيف نميز بين 2 و 3؟
There is a rule here, because here Between
في الرسم.
you mean how to determine the priority 2 and 3? Is this your question?
لا
ولا
الحين لما النموذج اللي عندك كيف قدرت واثنين وثلاثة؟
لا أنا عملت الموديل بأي طريقة كانت بس هو here. Alright, number, just imagine by any means, just let's just make any assumption. This is number 4. If you want it number 1, it's fine. It doesn't matter. This is a model. Do you follow me? Now, imagine this is number 4. Write it down in order not to forget. Black is number 4. Do you follow me? The one who was asking. Now, number 1 is the yellow one, in order just to show you how I decide. The yellow one is number 1. Alright? Number 2 is the blue one. Number 3 is the red one. Now let's make the model exactly as it is written on the board. Do you follow me? As it is written on the board, we have 2 groups which are on the same model, in the same plane. What are they? They are number 2 and 3. Number 2 is, we said, the blue one, right? So these are the 2 here. Can you see them? Blue is to my left, because it is to my left, right? When I look at here, it is to my left. And the red one is to my right, right? And then number 1 will be below here. And number 4 is above the plane, as you can see it. So this is exactly how it is, how it is looked like, how it is written actually in the board, as you can see it. Now, according to the rule, because again, this is just a model just to show you how to make the rotation. Now, this is number 1, this is number 2, this is number 3. I must view it from here. In order to make the rotation, we must go from 1 to 2 to 3, and then continue. 1 to 2 to 3. The result of this rotation is clockwise, and therefore the absolute configuration of this compound is R. I know it is a little bit, difficult to imagine, but remember, this is like passing through the neck of the bottle. Once you pass, that's it. You should be able to determine infinite number of absolute configuration of the compounds. But just imagine that these are all what we are talking about is simply IUPAC nomenclature. They are like nomenclature rules. So we must follow them strictly. We cannot put our own rule or our own logic, because that doesn't work. Because simply these are rules for nomenclature. You just first study them carefully and then follow them strictly. Then you must get to the answer. Is that clear? All right, let me make it again for another example, and this will be the last example for today, because you must practice actually at home, because without practicing you will never be able to get it. But as I said, once you get it, then this ability will stay with you forever. So let me just draw another structure, and then let's determine it together. Before I draw the structure, please, all of you, prepare a piece of paper and a pen and draw as I draw. So let's make it together, and a piece of paper and pen. All right, so let's make it like this. This is a 3-dimensional structure of a tetrahedral. All right, so we have Br here, we have, suppose, CH2, CH3 here, we have CH double bond CH2, and then we have CH3. Now, again here, in order to determine the absolute configuration, of this compound, we need to the first rule, we must determine the priority of the groups. So this must be number 1, this must be number 2, this must be number 3, this must be number 4. Again, I'm not gonna repeat how we determine the priority of the atoms, because this was the whole topic of the previous lecture. So if you don't know, if you forgot, just go back and study carefully the previous lecture. So this is the first rule. After we determined the priority of each atom or group on around the stereocenter, then we must simply view the molecule in such a way that the least priority atom is farthest away from our vision. So to do so, I just draw it on the piece of paper exactly as I have it in here. I write it. Please write it down as exactly as I write it. Just write it in big numbers, so on the whole page. So this here like this. Okay, I'll just make it the board with the marker just to show you. I will replace the atoms by the priority number. So this will be number, and then I will replace them actually using other color. So this will be number 1 is here. I'm not changing anything, I'm just drawing exactly as I see. And this is number 2, right? And then I have number 3 is above the plane, and I have number 4 is below the plane. Did you all draw it as you can see it in here? I did draw it. Some of you already determined. Anyway, let me do it together. And now, just follow what I'm saying, please. If you have drawn it exactly as I have done it on the paper. Now, where I have to look first, because this is extremely important, because this is a rule. We must view the molecule in such a way that the least priority atom is farthest away from our vision. So the only way to view it, actually, can you see here 1 and 2? It's between 1 and 2. So you must view it like this and look at here, then you will see it. So you can see it here 1, 2, 3, 4. Then this will be the angle. Let me just show you where is the angle. The angle is exactly in here. This, you must look at the compound. So this is your vision here. Do you follow me? Now, when you view it, when you look at it, and I am looking at it like you follow me? When you look at it, what you will see, just think of what I'm saying. Just hold the paper as I hold it. Do you follow me? Now, when you look at it, you should imagine number 1 to my left, number 2 to my right, and number 3 to above the plane. Now, the rule here, we must make or imagine a rotation between 1, or starting from 1, must go to 2 first, before 3, then 3. You follow me? Now, from 1, which is to my left, if you want to start from my left, if you want to start the rotation from my left, there is only 2 below the plane. If you go above the plane, you will meet number 3 before reaching 2, which is totally wrong then. Do you follow me? Because according to the rule, we must start the rotation from 1 going to 2 first, and then going to 3. And that's why we must go from 1, my left side, going downward in order to meet 2 before 3, because 3 is above the plane. I cannot go above because the 3 is above the plane. I will meet it first, which is wrong then. So the correct direction here will be from 1 going to 2, then continue to 3. 1, 2, 3. 1, 2, then 3. Do you follow me? This direction here, this is opposite to the clock direction, which means it is S configuration. Do you follow me? Again here, this is a fundamental issue. I know it is new to many of you, but without practicing, it's difficult actually to take it. So you must practice. At least practice today, and this is what I recommend you. At least practice to find out the absolute configuration of 10 different chiral compounds. This is a minimum actually in order to get the point in here. Now, once we have determined this, and then we said this is S configuration, so if we want to draw, what's the R configuration of this compound here will be? In order to draw the R configuration here, let me just make this. This was, I think, Br. This was CH, double bond CH2, and then we have above the plane, we have CH2, CH3, and then we have below the plane CH3. Now, this here, as we said, this is, just to check it out, S, yes. So this is S configuration. Now, if I ask you, for example, draw the R configuration of this compound, simply, if this is S, then the R configuration is just the mirror image. So let's imagine what's the mirror image of this compound. It will be like this actually. It will be Br here, and then CH, double bond CH2, and then the same thing here, which is CH2, CH3, and then CH3. Do you follow me? So if this is S, that means this is R, and these are non-superimposable mirror images, and therefore we call them enantiomers. So they are stereoisomers, which has a relationship of non-superimposable mirror images, and that's why we call them enantiomers. So this is R and that's S, and this is how we determine the absolute configuration of any or around any chiral center. Is there any question so far? Any question? All right. Now, sometimes we may draw the three-dimensional structure in different ways. We have different ways of drawing three-dimensional structures. I'm just going to draw them all. So three-dimensional structures. Now, when we want to represent three-dimensional structure around the stereocenter, we may draw it this way. So this is how we represent a tetrahedral, or we may draw it this way. Or we may draw it this way. Or we may draw it this way. So all of these are three-dimensional tetrahedral structure. And you must practice to deal with all these drawings, because you must know all of them, because all are with the same representation, which is the three-dimensional representation of or around a tetrahedral atom. Here, it's all just about three-dimensional structure, so it's the same imagination. Whatever you imagine, it will be always correct here. Now here, this here, when we draw it this way, this is what we call it Fisher projection. Sorry, Fisher projection. And the Fisher projection, and this is here, it's the simplest projection here, in which the three-dimensional bond, we don't show it, but we must understand this. Whenever we draw a tetrahedral this way, it means these bonds here, the horizontal bonds here, these represent atoms toward us, atoms above the plane, let's say. And these here, these are the atoms below the plane. لأن بكل بساطة هي simply you can imagine the tetrahedral in different ways. It's like these two are going toward you and these two are going away from you. Or you may imagine it like this here. Like these two in the same plane, one is above, one is below. Or you can see here this way. Like this is here, for example, this one. This is the same plane, this here, the same plane, and these two are toward you above the plane and this is below the plane. Or these here, you can imagine like these two, as I said, these are below the plane and these are above the plane. So all of these representations is the same like the three-dimensional representation of the tetrahedral. But as you will see actually in this book, in your book, you will see that the book or any actually organic textbook will use any of these. And therefore, you should be all the time able to imagine these three-dimensional representation and to determine the absolute configuration out any one of these. So I will rely on you that you will simply follow my recommendation, and you should today, not tomorrow, not after 2 hours, just simply after the lecture ends, you start right away practice of how to determine absolute configuration around any stereocenter in any forms written, either this form, this form, this form, or that form. Let me just highlight a little bit the Fisher projection, because we are going to use this exclusively in the second section, which is about when we talk about compounds containing more than one stereocenter. Let me just put it this way. Imagine a three-dimensional structure, and we have like whatever here. We have, let me just put it this way. And we have Br, we have hydrogen, we have methyl. So compounds like this, and we are asking you to determine the absolute configuration of this compound. Again, just routinely, we will know that after determining the priority, this will be number 1, this is number 2, this is number 3, and this is number 4. Then here now, we must imagine it, we must do the rotation and imagination according to the rule. We must view the molecule from this side, because that side is the farthest away from the least atom, which is number 4. When you view it this side, you will see it here this way. You should imagine now, according to what we have said before, these bonds, always any bonds written here, which means they are above the plane. So it's like the Br is above the plane, like this. See? Do you follow me? It's going this way. And we have 2 is below here, and 3, 2 and 3 are below the plane, like this. Now, what you will see here, or when you draw it here according to what we have seen, just draw it again, exactly like what I'm going to draw. Give me another paper. I'm going to redraw it again, and please, you all draw it accordingly. Just draw it on one paper, just one piece of paper. And here, you just mention only just mention only the priority atoms. So this is number 3, this is number 1, this is number 2, this is number 2, and this is number 4. Do you follow me? And just redraw it on a big piece of paper. And then I will set. And then we will do it together. Are you ready all to do it together on the piece of paper? This is exactly like what you are doing, what you did. All right. Now, according to the rule, what we said, according to the rule, we must the atom is farthest away from our vision, isn't it? So, according to the rule here, this is how it looks like, right? I must view it from this side. Do you follow me? So I just move the paper here from, as if you are, your vision, you must be near number 4 in order to, I'm sorry. Your vision here must be near number 1 in order number 4 to be farthest away from our vision, because that's simply the rule. So you must, or we all must, view the molecule from this side, from number 1, in order for here to be farthest away from our vision. Is that clear? Do you follow me? All right. So now here we look here. You just put your piece of paper as I look here. Now you have to imagine, because without imagination, this chapter is meaningless. You will never be able to understand it, because this chapter is all about imagination. And by the way, everything in science is about imagination. Your ability of imagination determines your ability to understand science. So always imagine. Imagination is simply science. Anyway, now, when you look at this compound from the angle of 1, what you should imagine that 1 and 4, we said they are above the plane, isn't it? Right? Now, which means 1 is above the plane here, because this is, remember, this is 3-dimensional structure. It's not a planar structure, it's a tetrahedral. So it looks like these 2 atoms like this here. So number 1 here is above my face, or above the plane of the paper. Do you follow me? Is that clear? Right.
دكتور
Yes, please.
الخط المستقيم ما يعني انه هو بالبلين
صح.
على مستوى البلين.
True. That's true when we draw other atoms in 3-dimensional. But here, this is called, as I said, this is called Fisher projection. In the Fisher projection, we only refer to the dimension of the atoms by just vertical and perpendicular. Do you follow me? So the perpendicular, this is the vertical ones. It means they are below the system, and the perpendicular ones means above the plane. Yeah. This here, this is the Fisher projection. We draw it like that, but with understanding of the 2 atoms here in this line is above the plane, and the 2 atoms here, they are below the plane if we draw it in the Fisher projection. This is special drawing, we call it Fisher projection. And in the Fisher projection, again here, any bonds, this bond and this bond means above the plane. This bond and this bond means below the plane. Is that clear what you have asked? The one who asked. Is that clear? No. So it's like a representation. It's like, this is agreement. This is, actually we do this, or Fisher projection has been made to make the life of chemists easier. Instead of drawing 3-dimensional and this is above, this is below, and so on and so forth, we just like agreement. Let's agree like that. Any bond in this line will be above the plane, like coming toward us. Any bond in this line will be below the plane, like going below or away from us. Do you follow me? That's simply our understanding, and that's simply our agreement. And from now on, whenever we draw it like that, it will be always the same meaning. So let's go back to Fisher projection again. So here, as we said, when we draw it in the piece of paper, we must view the molecule from number 1 in order number 4 to be away from us. So what we should think then, that this is when it's not as it is written in the paper, it is actually above the plane here, like going this direction here, like this. You follow me? So this is number 1, how it looks like. And that's number 2 and 3 is exactly, you can imagine them like that, but it's anyway in the same direction. So here, anyway, we need, according to the rule, we need to go from 1, which is the red one, on my finger, do you follow me? Going to 2 to 3. So how to go? There's only 2 directions of rotations. Either to go from here this way, or from here that way, right? Now it's very obvious that I must go from above the plane, going to my left side, and then continue the rotation. So it will be 1, 2, 3, 1, 2, 3, 1, 2, 3. This rotation is opposing the clock rotation, so it's counterclockwise, and that's why we call it S configuration. Is that clear? So this is S configuration actually. Any question about it? All right, thank you very much for following. But Hajar, Maria, what's your question, Maria and Hajar? Just interact with me, because it's not just enough to say no without interaction. Because if I wanna repeat it, no question, it's fine. But there is maybe someone else. Hajar, there is a question, Hajar. Okay. No, it's no problem if you have a question. But if you have a question, just interact with me in order to know what exactly the missing here. That's great actually that you are following me, and this is specifically, as I said, needs a lot of imagination. But it's like, again, I just want to highlight this. It's like passing through the neck of the bottle. Passing through the neck of the bottle is a bit difficult for the first time. But once you learn how to do it, you will simply go to a very spacious spoon here. Then it will be, your life will be very, very much easier actually. All right? So what I recommend you all to do after finishing this lecture, and this is even more important than attending the lecture, that you must practice by your own. You must simply view any molecule in your textbook, and there are hundreds of molecules in your textbook, chiral ones, and then simply determine its absolute configuration according to the rules. And you must all the time find that you have the ability to determine the absolute configuration of any compound, because again, it's not a secret that 99 of the questions of this chapter will be about the determining absolute configuration of configuration. Hajar, I don't understand your words. Are you following us, or you just want to mention something? Hajar, you have some question?
Doctor, I will just answer Aisha's question in the chat.
Sorry, Hajar, I didn't hear you well. Can you repeat it? Sorry.
Aisha is asking a question in the chat, and I was answered his question.
Okay. Sorry for that. So it's fine. The most important thing, just you are following me. Again, please, don't forget today we must finish this in order to move forward. Anyway, now let's move to another topic, which we call it compounds containing more than one stereocenter. So we have discussed so far what we have discussed, simply the compounds having only one stereocenter. So let's discuss of compounds containing more than more than one stereo center. Generally speaking, whenever we have a compound contains more than one stereocenter, there will be certain number of stereoisomers. The number of stereoisomers, actually it's written like this, maximum number of stereoisomers will be 2 n to the power, 2 to the power n. 2 to the power n. Do you follow me? Where n here is a number of stereo centers. Yani, in other words, if we have a compound contains 2 stereocenters, therefore the maximum number of stereoisomers should be 4. If we have, so if n equal 1, the maximum number will be 2. If n of stereoisomers, if n equal 2, the maximum number will be 4. If n equal 3, the maximum number will be 8. If we n equal 4, the maximum number will be 16, and so on and so forth. Imagine that, for example, if n equal 100, how much will be? Huge number of possible stereoisomers. That's why actually the beauty of this chapter is all about stereoisomers and the possibility of the stereoisomers. All right. So this is about the maximum number of stereoisomers. Remember, the maximum number of stereoisomers doesn't mean that in reality we must find it, but it means this is the maximum. There is no way to find more than this number of stereoisomers. In other words, if we have 3, the number of stereocenters in a compound is 3, then the maximum number of stereoisomers is 8. So which means 9 is impossible to be, 10 is impossible to be, but 7 is could be, 6 could be, 5 could be. In other words, this is the maximum. Anything else is fine, it could be in reality, but anything higher cannot be. This is the meaning of the maximum number of stereoisomers. Let's take specific example of a compound contains more than one stereocenter. So I'm just going to use, from now on, for this purpose, I'm just going to use Fisher projection. So remember from now on, in order just for simplicity issues. Now imagine here we have this compound. Let me write it first. 1,2-dibromo pentane. The 1,2-dibromo pentane is simply, when you draw it, it will be like this: CH3, CHBr, CHBr, then CH2, CH3. This is 1,2-dibromopentane. As you can see here, when you look carefully at this compound, you will see that we do have 2 stereocenters. This carbon have stereocenter. This is a stereocenter, and this carbon is a stereocenter. So we have 2 stereocenters in this compound. Therefore, the maximum number of stereoisomers of this compound could be 2 to the power 2, which means 4. What does that mean, 4 actually? It means we may find, in reality, 4 different stereoisomers represent this formula, which is 1,2-dibromopentane. Do you follow me? Just the only difference is that their spatial orientation of the atoms in space is different. That's all actually. Yes, please. What? 2, 4, 5. 1, 2. Sorry, not 1, 2. I'm sorry. Yeah, thank you very much. It's actually 2, 3. I'm very sorry. This is the example what I want to have. It's 2, 3. Thank you very much for the comment. It's 2, 3 dibromopentane. Please write it down. It's 2, 3 dibromopentane. Do you follow me? Now, let's see what are the structures then of what are these possibly here, these stereoisomers of the compound what we have. Now let's write the Fisher projections and the possibilities of them. Here we can do it like this. We may have, this is the carbon skeleton, so we have, for example, CH3, this is Br, and then CH2, CH3, and then hydrogen. This is one possibility. And this one possible stereoisomer, and the other one could be its mirror image, for example. Hydrogen, Br, and then CH2, CH3, and then CH3. And then we can continue later on. Let me just write them all. We can have Br, hydrogen, CH2, CH3, and then we can write the mirror image here again, CH2, CH3, hydrogen, Br, hydrogen, and then CH3. So these are actually the 4 possible stereoisomers of this compound. Now, to determine the absolute configuration, you must follow, for each stereocenter, you must follow the same rules what we have discussed before. I'm just gonna do it very quickly, and then you can do it at home. It will be like, for this stereocenter, will be like R. For this stereocenter, this here will be S. So this compound is R and S. Therefore, its mirror image right away, logically, its mirror image, always the mirror image will be the opposite of this absolute configuration. So if this is S and this is mirror image of that, this will be R and this will be S, and you can do it at home anyway. Now here you can see this is, we must do it this way. This will be like S, and this will be S. So that means this is R and R. So these are actually the 4 possible stereoisomers of this compound, of the 2,3-dibromopentane. By the way, this what we call it. We will call this is when you look at the nomenclature. We'll come to the absolute configuration later. But when you look at the nomenclature, this is carbon number 1, 2, 3, and 4. That means, and 5 of course. That means this will be. This is the absolute configuration of 2. This is absolute configuration of 3. So this will be 2R, 3S, then continue. What's the name of the compound? It is 2,3-dibromopentane. The same name of this compound is this one name, instead of only the difference is simply the absolute configuration in here. The same name is here, the same name, always the same name of the 4 compounds, yani the same end here. Like the only difference is this beginning. Here will be 2R3S, here this will be 2S3R, this will be 2S3S, this will be 2R3R. So this is 2R3R, and then continue the same. This will be 2S3S, and the rest will be the same. This will be 2S3R, the rest will be the same, and this will be here 2R3s. Do you understand me regarding the name? This is how it will be the APAC nomenclature of each compound in this structure or in this formula. Is that clear? Now, determining the absolute configuration around each stereocenter is a good practice for all of you. Do it at home today. Determine the absolute configuration here, this one, this one, this one. Just prove to yourself that this is really true. This is how I can do it, either in fission projection or any other three-dimensional structure. Do you follow me? Do it just today, because I don't want you to, postpone doing this. Now let's see. As you can see here, this and this compound, they are only mirror images to each other, and they are mirror images, and they are non-superimposable to each other. That's why we call these two enantiomers. This here, these two, we have again enantiomers, because again these two are mirror images to each other. Do you follow me? Because we said before, whenever we have a relationship between two structures, they are mirror images, but they are non-superimposable into each other. Then the relationship between these two structures, we call them enantiomers. So as you can see here, this structure and this structure, they are only mirror images to each other. But if you try to superimpose them into each other, they will never superimpose. Just imagine, just hold the structure as such and bring it in here. They will never superimpose, because simply the methyl will come to the methyl, the ethyl will come to the ethyl, but the brom here will overcome hydrogen, and the hydrogen will overcome brom, and this is vice versa. Hydrogen will overcome a bromine, and bromine overcome hydrogen. So therefore, these two structures are non-superimposable. So always remember, for any enantiomers, there are two conditions for two structures to be enantiomers. They must be mirror images. Secondly, they must be non-superimposable into each other. Similarly in here, you just take this here and then try to superimpose it. They will not superimpose, because the brom will come over brom, and brom here, hydrogen. Do you follow me? Is that clear regarding the enantiomers? And that we do have here four stereo centers in this compound, four stereoisomers. In this example, as you can see, we have two stereocenters, but regarding the number of stereoisomers, we have four, as you can see. And these two, we have two enantiomers here, we have two enantiomers there. So the total number of stereoisomers in this compound is 4. And that's actually related to the maximum number of stereoisomers possible in any compound. Is that clear? Any question about this topic, about compounds containing two stereocenters? All right. Now, just before ending, there is only just one relationship I would like just to highlight, and then we can continue the next lecture. Now, we know that the relationship between structure number 1, structure number 2, and structure number 3, and structure number 4. You follow me? We said 1 and 2 are enantiomers. Let me just rewrite it. 1 and 2 are enantiomers. 3 and 4 are enantiomers. What's the relationship between 1 and 3, or 1 and 4? What's the relationship between this compound and 3? Anyone knows? What's the relationship? What we consider the relationship between 1 and 3? We know 1 and 2, they are mirror images. They are non-superimposable, therefore they should be enantiomers. Then what about 1 and 2? 1 and 3? Anyone knows? Alright. Anyway, I will just write it down. As you can see, 1 and 3, they are stereoisomers. They are not the same. Do you follow me? I know, Ahmed, thank you. They are isomers, but I mean, they are stereoisomers. But they are not mirror images. In this case, any two stereoisomers, they are stereoisomers, but they are not mirror images. We call them diastereomers. I'm just going to erase everything. You can just write it down home. I'm just going to introduce a new relationship of stereoisomers. So let's just write it again first. Enantiomers, they are stereoisomers. They are mirror images, and they are non-superimposable into each other. So these are the criteria for enantiomers. There is another relationship between stereoisomers, which we call it then diastereomers. Diastereomers, they are simply stereoisomers. Any two stereoisomers, they are non-mirror images. Then we call them diastereomers. As if here, in this case, if you remember our scheme for classification of isomers, we may classify isomers this way. Isomers are divided into two types: structural or constitutional, it's the same, or stereo isomers. The stereoisomers, they are divided into two types. They are either to be enantiomers. If they are not enantiomers, then definitely they are diastereomers. Do you follow me? Now, so these are everything about the classification of isomers. Isomers can be classified into two types. They can be structural or constitutional if they are having the same molecular formula, but they have different connectivity of atoms. But when we have isomers having same molecular formula, same connectivity of atoms, but only the difference is the spatial arrangement of atoms in space, then we should call them stereoisomers. The stereoisomers are still and are further divided into two types. They may be classified into enantiomers or diastereomers. The enantiomers, as we have explained before, the stereoisomers, they are any two stereoisomers which are mirror images to each other, but they are non-superimposable into each other. Then in this case, we call them enantiomers. If any two stereoisomers, they cannot be classified as enantiomers, in other words, they do not fulfill the criteria to be considered as enantiomers, then they are definitely called diastereomers. Do you follow me? All right, I think it's enough for today. Next time, inshallah, we will finish the remaining of this chapter, and then right away, inshallah, we'll start a new chapter. By the end of this week, you will find on the model there will be assignment for some problems related to chapter 5. The exam grades will be announced today, inshallah. I have finished marking of the whole exam, and it will be It will be announced today. Cut. The only thing